In this video, I'd like to talk a little bit more about these graph data structures. So remember that graph data structures might look something like this, where it's a series of nodes and then the connections between those nodes. And these nodes can represent anything we want them to represent. E, F. Let's imagine we have a graph data structure that looks something like this. And these could represent airports or positions I can move through in my world. They could represent skills inside my skill tree. One type of graph that is really common is a directed graph. A directed graph is one where each of these connections has a single direction associated with it. So for example, each of these connections has, it's kind of like an arrow, right? C has this directed connection to A. A has a directed connection to B. A has a directed connection to D. It could look something like this, right? It could also look something like that, where these connections have multiple directions associated with them. So D is connected to E, and E is also connected to D, right? This is the idea behind a directed graph. This could be used for something like, back to that example of airports, maybe Chicago has a flight to, flight to A, whatever A might be, and A doesn't have a flight back to Chicago, right? There's only one direction you could fly in between these two airports, right? But D is connected to E, and then E is connected back to D, right? So it's sort of representing that you can traverse either direction here, right? If this was something like a 3D game world, and we had walls here, and we were planning on using this graph data, for some sort of like pathfinding logic, right? If we had a building like this, and we had our AI moving around within here, and we wanted to represent where our AI can move based on this graph data, maybe this D to C, maybe there's like a hole right here that the AI falls down. So you can only go in this direction. You can climb down, but you can't climb up. Same here. Maybe you can continue falling downward towards A, but you can't make your way back up. And then A, you can traverse to D, but you can't get back towards A, right? There may be like a hole in the floor over here where A, you can fall down and you can get to B, but now you can't climb back from B, right? So you kind of get stuck over here. So this is where a directed graph can really come into play and really help us. The next type of graph that I want to talk about is something called a weighted graph. Now, a weighted graph is one where all of the connections have weights associated with them. And you can imagine this being important if you had a graph that looked like this. Here's node 1, and here's node 2, and here's node 3, right? Node 4, and node 5, and then finally this connects back to node 2, right? Maybe something like this. So this is a directed graph because each of these arrows has a direction associated with them, even though I've made it bidirectional, each one of these connections. I'm just creating sort of this oval shape so you can traverse in either direction along each of these nodes. And one thing to note here is that the connection between 1 and 2 is much further apart. So if this was the graph that was representing a 3D world that we wanted to traverse in one of our video games, or if this was a graph that was representing airports and flights, we might want to represent that this connection here, the flight between 1 and 2, actually takes a lot longer than any of these other smaller flights. In which case we might want to say, you know what? The flight between 1 to 3 is actually, this is a 1-hour flight. And between 3 to 4, this is also a 1-hour flight. 4 to 5 is a 1-hour flight. 5 to 2 is a 1-hour flight. But between 1 to 2, this is a 6-hour flight, right? This flight takes 6 hours to go back and forth. And then you might ask yourself, well, which way should I walk? Which way should I fly? Which series of flights should I take? Based on the fact that this flight is so much longer, right? If we ignore the idea of takeoffs and landings and layovers, in this example, it's easier to see that even though you need to go between more airports, there's only a 4-hour travel time to go from 2 to 1, even though there is a direct connection between 2 to 1 along this connection here. So this is where a weighted graph might come into play. We use it to represent how hard it is to traverse from one node to another. Inside our example here, if we were using this as a way to pathfind around a world, we might actually say that this traversal going down here may be something where it's more severe than the traversal here, in which case this might have a weight associated with of 1, but maybe moving along this path may have a weight associated to it as like a value of 3. For anyone who plays Dungeons and Dragons, this actually might seem very familiar to you. In Dungeons and Dragons, it's a tile-based game, but it has this idea of rough terrain. And so even though it's set up on a grid, you have some squares that are considered rough terrain, and it's harder to move through those tiles. Those tiles essentially have a higher weight associated with them, right? Even though if I drew out a grid that looked something like this, my very poorly drawn grid, if I was standing at this position and I want to move to this position, it may actually be faster for me to go this way, longer to go around, than it is for me to cut right through this tile, which is rough terrain, because it's harder for me to move through this space. This here is representing something that's very similar to a weighted graph. And in fact, graphs can be used to represent grid data. A graph to represent a grid is simply one that looks like this. This is a 2x3 grid. And if I want to represent rough terrain, I could do so by just having weights associated to each of these connections that might be higher. This connection is a 2, and this connection is a 2. All these other connections are 1. This is really similar to this section up here that I drew, right? I've got 6 nodes, and I've got 6 nodes here, and the connections going from these positions over is actually more severe because I'm entering rough terrain. Down here, it's harder for me to make that traversal because the weight is higher. So graphs, especially when you add in this idea of directed graphs where these connections can go either ways, as well as weights associated with our connections, can represent some really cool, complex stuff that you might not be able to represent well in other data structures.